Hi, good afternoon or good morning, depending on where you are. My name is Robert Schoenberger, editor of today's Motor Vehicles for GIE Media. I'd like to welcome you to today's IMTS conference, How to Leverage the Digital Twin to Optimize Datum Features and Validate, and validate geometric dimension and tolerancing in order to reduce manufacturing costs and lower the risk of defects. We have two speakers today. Maria Arenas is Senior Dimensional Engineer at Finite Element Analysis, FEA, Specialist at DCS, Dimensional Control Systems. An experienced engineer with more than 20 years in dimensional and FEA expertise, she has led initiatives and projects in the aerospace and defense, automotive, heavy industry, high-tech electronics, and medical device industries. As the FEA specialist at DCS, Maria provides training, guidance, product management, and modeling with a focus on compliant and material studies. And Paul Vickers is dimensional engineer, engineer and GD&T specialist at DCS. A design for Six Sigma Master Black Belt and former General Motors DFSS Global Process Guardian, Paul led the global DFSS team developing people, methods, and tools. Paul developed tools and methods for product and process fit, finish, and function for GM's global Delta platform, vehicles such as the Chevrolet Cobalt and Saturn Ion in North America and the Opel Astra in Europe. Paul led development of GM's global bill of process, lowering piece cost, investment, and mass while improving quality. Paul recently joined DCS to provide GD&T consulting and training to DCS clients and assist in the development of new tools for tolerance analysis. If you look at the bottom of your screen, you will see a tab next to participants that says Q&A. If you have any questions for the speakers, please type them in there and we'll ask those at the end of the session. Or you can also use the chat function, but it's much easier for us to track this in the Q&A tab. With that, Paul and Maria, the floor is yours.
Well, thank you, Robert, and good afternoon or perhaps good morning to those of you on the West Coast. As Robert said, my name is Paul Vickers. I'm a developer at Dimensional Control Systems. Maria, if you can go to the next slide and another one, please. Yes, DCS, or Dimensional Control Systems, is a world leader in the war on variation in manufacturing. DCS develops and distributes software solutions to help you throughout your product development lifecycle. 3DCS tolerance analysis software and QDM for SPC, quality data management, work together to provide a cradle-to-grave solution and coverage for your organization. I'm proud to be here today to introduce an exciting new function in the DCS software suite of solutions, the 3DCS Datum Optimizer. Next slide, please. The 3DCS Datum Optimizer is a unique combination of state-of-the-art CAE tools, including two that you may be familiar with, the 3DCS variation and analysis tool, the 3DCS compliant modeler, and our newest tool, the DCS genetic algorithm. Next slide, please. A little bit about each of these to try and frame this up and make sure we're all talking the same language. The variation and analyst is a tool that enables you to analyze the effects of part tolerances and assembly methods on dimensional quality. You can find and fix problems before they hit the factory floor. Included in the 3DCS VA, Variation Analysis Toolkit, is a Monte Carlo simulator that allows detailed statistical analysis and problem identification as shown in the image on the left there, where we simulate many parts and then we can do analysis and statistical analysis, including histograms like this. You can see that there is a lot of production out of specification. We have a mean shift problem, etc. Then DCS VA has a number of analytical tools to help you analyze the problem, such as geofactor analysis that can help you to identify solutions and improve your designs quickly, as shown on the right. So we went from what's on the left a lot of red, to what's on the right, where we have most everything in green. Next slide, please. The 3DCS FEA compliant modeler blends the tolerance analysis with finite element analysis to allow you to measure the impact of product stiffness or external forces such as clamping or welding or bolting or gravity, and all those could affect your dimensional quality. These tools have been out for a number of years. What we've got is a new tool. The next slide, the genetic algorithm, is a optimization tool that allows us to help you find better solutions by automatically creating new product or process alternatives and evolve the design to better and better solutions. It's kind of a Darwinian development where only the strong survive and the weak are eaten. So we'll talk a little bit at more length about how we applied this to the datum optimization problem as the presentation goes on. Next slide, please. So we're here today, well, we're here virtually, I guess, to discuss the 3DCS Datum Optimizer. Let's start at the beginning, which seems like a good place to start, and just make sure we're all on the same page and talking the same language. Datums are fundamental and the foundation for dimensional management, dimensional control, and a key to variation reduction. Datums are used throughout the manufacturing process to locate parts, assemblies, and or the final product, to machine the product, assemble the product, join things together, and in measurements and measurement analysis. Proper use of datums creates a well-defined coordinate system, as shown on the right, which enables you to locate features in their proper orientation and position. Datums are key to managing and minimizing variation, the enemy of quality. And as shown here, we've got 3 planes. We just call them datum plane A, B, and C. They use what is commonly called the 3-2-1 locating system, which we'll talk about a little bit more later, where the 3 points form a primary plane, which constrains 3 degrees of freedom. 2 points form a plane, the secondary plane, perpendicular to the first plane, which stops 2 degrees of freedom. And then the tertiary plane can be formed by 1 point. It is built perpendicular to the other 2 planes and restrains 1 degree of freedom. So we have all 6 degrees of freedom constrained with this 3-2-1 locating scheme. Then from that datum scheme and that measurement basis, we can measure anything in terms of its location, position, or orientation in space. Next slide, please. So what we're going to do is illustrate our new feature, this 3DCS Datum Optimizer. We wanted to choose a product that everyone could kind of understand and is familiar with, such as an automotive fender, because everybody's seen an automotive fender. If we had picked up a different part, a more complicated part, like say a flux capacitor, we might have to spend more time explaining what the part is and how it works. We'll just pick something that is on almost every car, or at least the new ones, because in my neighborhood there's a few cars running around without fenders, I'm sure. Fenders are fairly large, yet they're thin-walled. They are both stiff and flexible. If you lean on your fender too hard, you'll see it's not too stiff. You might dent it. And before all the attachments are made, it really is quite flexible. And you can move it around a little bit, and then it gets a lot of its rigidity after you join it to the vehicle. Fenders also interface with a lot of the vehicle. You know, we've got a interface to the door and the hood, the lamp, the fascias, the tire envelope. It interfaces with quite a number of parts. And as automotive manufacturers seek to have jewel-like quality. That means precision fits between all of the parts. The fender is one of the key components. Next slide, please. So the following slides will describe a typical project flow and show how 3DCS tool suite, variation analysis, compliant modeler, and the Datum optimizer work together. So typically, we start with with a team of people who have selected some some datums and tolerances for the fender and the parts around it. They do that with some best practices or their experience or whatever, and then they do some analysis. So 3DCS variation analysis was run to predict dimensional quality, and we get a plot. We can get one of our many plots, might be a histogram like I showed before, or this color plot where you can see how much variation we have around the fender. Red is high per the scale on the right, and then blue would be calm and low. What we would like is everything to be blue. Very little variation. Anywhere you see the red, we are having bad fits to the mating parts, which in this case might be the lamp and the fascia. Next slide, please. So, you could say, Houston, we have a problem. What we've got is we have a number of parts that aren't meeting the specifications. We've got some mean shifts. We've got some excessive variation. We've got part distortion because it's not rigid, etc. And so that can be summed up by showing, in this kind of graph we've got here. It illustrates the large variation, the mean shift. The green is in spec, the red is out, and we got a heck of a lot of our product out of specification. Now, the team suspected that the datum scheme was part of the problem, and we will show they were right. And so they thought if we could find a better datum scheme, we could change the scheme and only the scheme, not the tolerances, not the attachments, just the datum scheme. And we could reduce variation, eliminate or minimize the twist and the mean shifts, and bring the part back into specification. And on a side note, just as it says there, poor R&R performance, reducing variation could enable the measurement system to pass gauge R&R. That's the repeatability and reproducibility, a key step in our product startup at start of production. Next slide, please. Now, we could locate the part many, many ways at many different points, and then we can combine these many different ways to locate the part. They picked the ones they've always used, and they got the results that you saw before. What if we changed? What if we moved from one part of the fender to the other to locate them? Now, the problem, and it's a business problem, is there are so many alternative datum schemes. How can we find a solution quickly? So if you go to the next slide, this sounds like a combinatorial problem. So therefore, we could quantify the number of alternatives. And I'm sure you all remember from statistics class, the combination formula shown here, C sub n sub r, which calculates how many ways you can combine n factors. That would be the number of potential datums. R ways, the number that we're going to use in our study. Now, this isn't math class, so we're not going to ask you to solve the formula or remember the formula, but we've give you an idea of the magnitude of the problem with the table we've shown on the left here. The first column is the number of datum candidates we have, the number of different ones we could choose, and then the number of datums we will use is shown in the second column. And then the number of combinations is shown in the third column. If you had 20 candidate locations, we wanted to use 6 datums to maybe over constrain our primary datum. We'll talk about that a little bit later. There's about 40,000 possible combinations. If we had 80 candidate points, we're only going to use 3 for our primary plane. There's 80,000 combinations. And that's way too many to do physical studies, way too many to do in CAE. So this is really why we created the 3DCS Datum Optimizer. Next slide. The Datum Optimizer, or DO, just do it as we call it, provides the means to set up and run the combinatorial problem in just a fraction of the time, as we'll show you in a demo at the end of my, after I'm done talking here. For any part, you select your part or assembly that you want to analyze. Then you can choose whether you're going to do a rigid part or compliant part analysis. I'll talk a little bit about that in a minute. And then you provide the candidate locators. Where on the part could we put a datum? And then the DCS Datum Analyzer will do the analysis for you and display the results. Next slide, please. A quick note on rigid or compliant analysis. I talked a little bit about this. As I described earlier, datum schemes are usually set up in a 3-2-1 formula. 3 points form a primary plane, constraining 3 degrees of freedom. 2 points form a plane perpendicular to the primary plane, constraining 2 degrees of freedom, and 1 point forms the tertiary plane and constrains the last degree of freedom. And this is great for very rigid parts or very solid parts, maybe an engine block or something like that. However, many parts may be thin-walled and are compliant, kind of like our fender we talked about. Then you might want to add additional locators to help stabilize the part. So you might have a 4-2-1 where the 4 points are constraining the part in the primary direction, or maybe 5-2-1, 6-2-1, etc. You are over constraining the part, and the Datum Optimizer will do this for you. Next slide, please. Once you have set the part up, we've got our part, we've got our candidates, we've decided whether we're going to do rigid or compliant. We've decided, are we going to do 3-2-1, 4-2-1, 5-2-1, or look at all of those. Then we use our genetic algorithm. The genetic algorithm creates new datum strategies and evolves the design to better and better datum sets. Only the best candidates are chosen to reproduce, and the parents' genes are then mixed, and then the offspring are evaluated. If they are better and are more stable and give better dimensional results, we keep them and they are allowed to reproduce. And if they are weak, they are not allowed to reproduce and they die off. It's a survival of the fittest game. And then as the generations go by, the design gets better and better and better. Next slide. The DCS genetic algorithm helps us be really kind of efficient at doing this. As shown before, the number of candidates in column 1, the number of primary datums, column 2, and the number of combinations we saw before is in 3. Well, the nice thing about the Datum Optimizer is we have constrained the number of runs, and through our testing we realized we converged to our great solution quickly with the number of runs shown in the 4th column, and then the ratio of the full factorial or total number of potential runs to the GA runs is shown in the right. You can see we're computationally efficient. All right. Note, there is a note on this. I just want to point out that GA is like all optimization strategies I know. The only way to guarantee true global optimality is to run all the combinations. DO normally finds the true optimal, but in a small percentage of cases, it could converge to a number or to a datum set that is not global optimal, but it will always converge on a great solution near the global optimal. So I just want to be clear, we're not guaranteeing perfection, but we're guaranteeing a pretty darn good answer quickly. That's the bottom line of this slide. Next slide, please. Now, recall if you select compliant model, Datum Optimizer will solve best 3-2-1 as well as 4-2-1, 5-2-1, 6-1. You can ask it to do that, and then you can see you get results like you see on the bar chart on the right, which shows how much variation we have if with the best 3-2-1, that's the far left bar. As you add constraints, such as a fourth locator, variation is reduced and it gets better. That's the one next to it. It's a little bit lower. Adding a fifth reduces variation, and so does a sixth, the one on the right. Next slide, please. Now, as expected, adding constraints does reduce variation, but each additional constraint is not free. It costs tooling money and potentially some process time, certainly maintenance, etc. So we want to make sure, since we're spending more money, we want to make sure we're getting some bang for the buck. What's nice about the DO, it shows the point of diminishing returns and the value you get for each incremental tool cost. I can say if I go from 3 primary locators to 4, this is how much variation is reduced. If I go from 4 to 5, this is how much it costs, and this is what I get for it. 5 to 6, etc. So we can get business value out of knowing what we get from the optimal numbers. Next slide, please. Then DCS is the Datum Optimizer is integrated with the full DCS variation analysis toolkit and other DCS tools, allowing you to use the functionality to illustrate your results, sell your solutions, such as the color mapping we saw here. As we talked about before, on the left is where we started, and there was quite a bit of variation, some variation of 4 or 5 mils. And then, as I mentioned before, red is bad, blue is good and calm after we went through the Datum Optimizer, and not a huge difference in all of the locators, but a difference. You can see that the Fender delivers much better dimensional performance for the same number of locators. So, as we promised earlier, changing only the location of the datums, variation can be reduced, part distortions can be minimized, and we don't have to spend money to do it. So this is the great thing about datum optimization. Now I'm going to turn the presentation over to my friend and colleague, Maria Arangues. And she is going to talk about how we solve these problems. We go from large variation with significant mean shifts to reduced variation, no mean shifts, percent out of spec reduced or eliminated, and increased likelihood of passing our gauge R&R. Maria, please take over for me.
With pleasure. Hello, everyone. I'm going to show you an example of a fender, which we've been talking all this time. Paul has actually. Before I get there, Paul mentioned that there's 2 types of analysis with a datum optimizer. One is rigid, one is compliant. Each of them has 3 options of doing the calculation. We can minimize the maximum variation for rigid or deformation for compliant, and that means you look at all the points on the fender that were added, which have a certain role and importance in attaching the fender, and you minimize the maximum value of those points as far as variation or deformation. You can also do an absolute average and minimize that absolute average of the same all points with the second option. of calculation, or you can use certain measurements that were created around the part and optimize for those measurements. And with that, I'm gonna show you the, give me a second. I'm gonna start with a model. So what will we have? This is a 3DCS model, and it has one part involved, the fender, and some empty part that represents the attachments, the body and white attachments for the fender to its corresponding parts. Basically, the rail here, it will be gapped to the door. It can be gapped and flushed to the headlamp and to the fascia, and adjusted around the wheel house. We have points created in the fender. There's different sets of points. We created 7 points for potential datums and locators in X direction. We have 10 for Y direction and 8 for Z direction. We also have points created for the assembly measurements, the measurements that we'll use later to do different calculation. These measures are gap and flush measurements around the fender. And there's also some extra points just to throw them in. They are not used as potential locators. They're not used in measures, but they're also on the fender. So we will consider an initial potential locating scheme for the fender. This is a rigid move. This rigid move uses 3 points for the primary direction. I'm gonna move this to the side so we can see it. 2 points for the secondary direction, which in this case is Z, and 1 point for tertiary. These 6 points will fully constrain the fender to features on the fictitious body and white. And if we say, let's say we build the model with the rigid move and we run some simulations, let's say we run 2000 assemblies, we will get some results for, we have one single measurement. The measurement that we're seeing here, it's shown on the graph with all these lines. Basically, we have measurements all around the fender. The measurements are for all these points. We have 68 measurements for every point that it's on the fender to corresponding point that's on the body and white. These are distance measurements. So we measure basically the maximum of all distances between them. Now, if we look at the estimated range and estimated high, they're somewhere around 1. So what I'm gonna do, I'm gonna change the scale for deviation here and make it 1. And then I'm gonna say, show me the maximum of this measurement. And it shows me some red in this area. So let's keep this in mind and then go to the datum optimizer and see if we can get a better scheme than this. Datum optimizer is part of the add-ons modules of 3DCS. It's part of the advanced analyzer and optimizer. And I'm going to click the icon to open it. You've seen this dialog in the presentation before. This is a rigid study, so we're going to start with rigid. It's pretty easy to use. First, you have to select the part that you want to optimize. So I'm going to click on the fender. Then you're going to optimize what kind of calculation you want. So I'm going to say minimize the maximum of all variation. That means every single point that it's on the fender, it will be taken into consideration, and the variation for each of them will be considered. Now I'm going to pick what we call candidates and constraints. Since I picked them earlier, they're already in a list. And I have 10 for secondary direction. I have 8 for, 10 for primary direction for J, I have 8 for secondary direction, which is in K or Z, up, down. And I have 7 candidates for my tertiary direction. Now, for simplicity's sake, I'm going to say keep my secondary and tertiary. So I'm going to pick and fix 1K and 5K and 9I, just like here, just like in the previous move. Once I fix these, I'm going to optimize just for the primary direction. I'm going to say OK. And once we picked all of these, the objective function, the part, the candidates, we can look at the bottom of this dialog, and we see that we can run optimization with a genetic algorithm, or we can run the full factorial. This one is shorter. It's 120 samples. That's because we said I don't want to optimize for secondary and tertiary. So optimizing just these 10 points, it requires 120 calculations. This is probably under 1 minute. I am not going to run it because I already have the results. So I'm going to load my results that I previously ran, and I'm going to load the rigid. And what do we have? We have 120 runs for the full factorial. And here I have my results, what I was looking for. And I kept the 1 and 5 and 9, right? I kept my secondaries and tertiaries the same, and I'm optimized for the primary. Now, we can also say, okay, what happens if I choose the 111? If I choose the 111, I get obviously a different optimized number, a different set of optimized datums. So going back to 120, I prefer to get the best suggested. And what I did after this, I created another move with the datums 4, 5, and 15, just like it's shown here. It's exactly the same type of move, except 3 different primary locators, which are suggested datums than initially. So once we have this, I'm going to activate that move. I'm going to nominal build, and I'm going to run the simulation again, 2000 samples, see what we get. And let me minimize the datum optimizer for a little bit and put the new run below here. If we look at the variation, initially the estimated range is 0.899, then the optimized is 0.754, slightly better. So what is my maximum in this case? It doesn't show me any red, like, let me see, I have to go and activate each move in order to apply the maximum. So remember, initially we had a little bit of red corner here. Now that red corner is gone. So we did optimize the rigid, and the rigid is calculated based on best suggested datums. When we applied basically a surface profile tolerance on all the body and white features that come in contact or are measured from with the points on the fender. So the variation comes from attachments on the body and white, for these points or features that we measure to. Okay, rigid is nice, we made it better, but we have to remember there's other things that happens with a fender when you attach it, like gravity. So I'm gonna close these two, and I'd like to take this a step further. So I'm gonna bring up my Datum optimizer, and I'll say, okay, let's see what happens if we let this sag due to gravity. For that, we need to use the compliant. The compliant is similar to rigid in the sense that you again select the part. I selected the fender, and when I selected the fender, you've noticed that I have populated fields here like gravity, and gravity direction is -1, so it points down as expected. Now for compliant, I can pick more than 3 because I can over constrain the part in a primary direction. So let's say I want 4. Then you observe here another set of fields which says FE files. What is this? It's reading the information. Basically, it's reading it from this move, which is specific to compliant models. And it reads the information from Abacus for a mesh file, for its stiffness matrix, which has to do with the deformation of the part, how the part deforms, and its mass matrix, which has to do how gravity is applied. So to apply gravity, we need the mass matrix, and to deform the part, we need the stiffness matrix. These files were created before, and they were loaded in the model here. And when we select the part in Datum Optimizer, it reads them and it uses them. Similarly, we do a minimization of maximum. In this case, it's deformation because we only apply gravity, so this causes the part to flex. And we're not using repeated assemblies for this study, just see how much part sags due to gravity. For this kind of calculation, I want to run the optimizations. Even though full factorial is shorter, I just want to see how my optimization does. But I also want to say, I'm going to go to my candidates and constraints, and I'm going to say, I don't want to constrain the secondary and tertiary. I want to optimize everything. I want to do a 6 DOF optimizations in all 3 directions. Now, once I uncheck those, do you see my full factorial? It's much larger. So I'm definitely not going to run that. I'm going to run the optimization. I did run it before. It took about 1.5 minutes. So I'm not going to keep you guys here. I'm going to load the results for the minimization of maximum deformation with optimization. So what do we have? We ran a set of 4 best optimized datums, and we got a bar that shows us the value of 0.584, which is right there, close 6. And it shows us what the suggested datums are by the optimization. And we have 4, 6, 10, 12, and we have different for secondary. So if you look at the initial, we also create an initial move for, I'm going to activate these moves. We use this for secondary direction and tertiary. So we attached here and here for Z direction, and here I want it gapped to the door. So that's my tertiary direction. And we use another operation, a clamp, to attach it in primary direction. There's 4 attachments, so the fender is clamped and it's over constrained in Y direction. Now these are the initial numbers. With the initial numbers here and applying the gravity, I'm going to activate the gravity. I'm going to do a nominal build, and whoa, it's all red. Why is it all red? Because my measurement, it's 5.4. So what I'm going to do, I'm going to change my scale here. For color contour, I'm going to make this 6. And I'm going to nominal build it again, basically apply the gravity again. So once I apply the gravity again, with these initial moves, you can see we have a section of red here, which gets basically to 6 mil deformation. Let's say we ran the optimization, we got the results, we got these new suggested datums, and I'm gonna use those in the move. So I created 2 separate moves. A third move for using 5.7 and 5i for the secondary locators, and this over constrained again for primary locators. So I'm going to swap these moves and activate my suggested optimized moves. And I'm going to say nominal build. Once I nominal build it, everything is nice and pretty and blue. And looking at the maximum value, it went from 5.4 to under 1 millimeter. So by changing the locators from that set of numbers to this set of numbers, we reduce a lot of deformation in the part, a lot of sag that happens due to gravity. There is another way that we suggest that you optimize your results, and that's valid for rigid and compliant. I'm going to demonstrate it for compliant only. We want to do a minimization of selected measurements. What does it do? It allows you to pick some measurements. And in this case, I want to pick these measures, which are all distance measurements from the body and white to the fender. And they're gap and flush measurements, basically. Once I pick those measures, it's going to solve for these measures. Now you notice there's this column that shows all my measurements, all 33 of them, and they're all around the part. And I have the second column, which is called weights. In this case, I give the same importance to all of my measures because they have all the same weight. You can play with this number, make it smaller than 1, and it makes that measurement less important if you think that's the case. Once we picked the measures, I'm going to use the same candidates and constraints. I'm not going to change this in any way. And full factorial, again, it's a large number, so I don't want to run that one. This takes, again, less than 2 minutes. We also want to solve for 4 datums, primary datums. So I'm going to load the results for that particular case, and it's this file. What does this file tell me? It gives me a slightly different combination than the one that I used when I optimized for all points. Basically, this is like a smaller set of conditions to optimize for. So the secondaries are 5, 7, and 10 instead of 5, 7, and 5. So it wants me to use these 3 for secondary, where I have this for Z, and this is for X. And the primary, it's 4, 7, 10, 12 instead of 4, 6, 10, 12. Okay, so second point goes from here to here. Now, let's see what happens. So if we look again at the last results, the measurement, the maximum value we got was 0.775. Now let's say we activate the last set of measurements and deactivate the first ones, and we now build and see what happens to the part. It's still blue. Change the blue color a little bit, but let's look at the numbers. So from 0.75 to 0.68. So this is a little bit better. And remember, we check everything around the part, not just the measures that we used to calculate. So we optimize for a set of measures and we got an overall slightly better result. From 0.75 to 0.68, it's really not a big difference. If you venture yourself and want to run full factorial, I believe this is a smaller number than the previous one. When we ran the minimization of max deformation. So it should take a little bit less, but it will still take a significant amount of time, which you probably don't need to do anyway, because given that our initial results were, let me remind you, close to 6, and any of these, either when you optimize for all the points in the part or you optimize just for a set of measures, they both go from, let me see, from 5.4 to under 1 millimeters. Either of them, it's good. And you want to do these scenarios because sometimes you can't use these points. Sometimes there's one of them is not available for whatever reasons, it's not reachable, so you use a different scheme for that. Same goes for, if you look at in the Datum optimizer, we have first optimal, we have second optimal, and we also have a third optimal. So we give you 3 options of 3 sets of points that in case the first one doesn't work for you, you have other options. And I believe this is all I had to cover. So if anybody has any questions, please feel free.
Thank you very much, Paul, Maria. It's a great presentation. And like I said at the beginning of the presentation, if anyone has any questions they would like to ask of the panelists, just go ahead and enter those into the Q&A tab at the bottom of your screen. We have a few to start out with here. This could go to either one of you. How critical are the selection of datums to the design dimensional engineering process?
Paul?
Well, it's the foundation for dimensional engineering, is the proper selection of your datums. And I think as Maria showed here in live time, you can make some fairly significant differences in dimensional performance, changing nothing but the datums. So I think in most dimensional engineering organizations, selection of datums is job one. And then we worry about the tolerances and everything else. So
you talked a lot about this being a genetic algorithm. Is this an installed application or is this a cloud-based? Because I've seen genetic algorithms are pretty popular in cloud applications.
Well, I think it's installed. It's not a cloud-based.
Okay. Mainly with sorting problems, it seems that the ability to run simultaneous simulations tends to, this is a little more math intensive. So, all right. So besides tooling costs, what are some of the disadvantages of having more datums than needed?
You also have process time, more things to break, maintenance, etc. So you want to, the goal is to have minimal tooling. That would be great. Right? Less capital cost, less operating costs, less maintenance, less things breaking. So you want to get to the minimum. But sometimes you can't go to the minimum. You have to you might need more than 3 to 1.
Maria, you talked a lot about this, but how long does it take to make a datum optimization model? How long does it take to run that model?
Well, it's not a lot if you think about it. The most time it took me was to create the measurements. Probably a couple of hours.
All right. And last time, who's using 3D CSS these days?
Okay, we have a lot of people that use 3DCS. I'm gonna give you a list of names that people that companies that reduce the manufacturing time using 3DCS, and these are just a few.
Mm-hmm.
On our webpage.
Phillips, yeah.
Yeah.
So some names I recognize on that list.
Yeah. Yeah, automotive, medical, aerospace, machine tools. So they're across many industries. I think, as Deming said, variation is the enemy of quality, and that goes for every organization that produces parts.
And Paul, you might be able to speak to this a little bit. You mentioned early that some of the tolerancing has gotten tighter over the years as companies are moving towards the more jewel-like fixtures on vehicles. With the increased interest in electrification and the need for better noise performance, is that becoming a bigger issue? The gaps, the body gaps, and things like this, when you have no engine noise to drown out the sound coming from the road.
I haven't really put a connection between those two. Although I will say that some of the fits for wind noise has become a bigger problem. So you have to have better fits between some of your closures, and you have to anything that the air flows over, mirrors and things like that. Much more important as we've reduced the amount of engine noise. We still have the road noise and wind noise. But I haven't seen a connection between fits other than this constant push to get better and better looking vehicles. So.
All right, great. That looks like our time for today, and also looks like the questions. If people have any more questions, I believe Maria and Paul's information is available up on the IMTS Spark website. This presentation has been recorded, so if you want to go over the information again later, this will be posted on the IMTS site soon. Thank everyone for attending today, and have a great afternoon.
Thank you for the opportunity, Robert.
Thank you.